transformation of the experimental data from the graphics to numerical form is a very important question. And usually what we may see from the literature is some graphic from the book. These graphics I took from the Anderson book. I just bring to front, and this is it. This is the data. There is no tabular form. There is just this data, and we need to somehow transform this data into numbers to have possibility to compare this with our calculations, with our calculation results. All right. So we can do the following. There are several programs you can do inside CACHI. You can use MATLAB, I'm quite sure. But today I show you just how to make it in Microsoft Excel. All of us have access to Microsoft Excel as staff and students of the University of Brasilia. You know, it's free for us. So based on this free instrument, I'm showing you how to make the numerical representation of these values. What I do, I create a table. This table is composed of two columns. Alpha column is the angle of attack, and here will be, for example, my CL coefficient. And I write some numbers here on the alpha, which I suppose would be close to my experimental results. I already prepared it, so it's very, very close to experimental. But just looking by eye, we can write some preliminary numbers of alpha, and we can write some preliminary numbers of the lift coefficient. And then we are taking this data and we insert a new graph, a new chart, like this one. Very simple scatter chart. I will not create because I already have created this chart here. And I make background transparent. And behind this graph, I put my picture, which I took from the book, from my reference. And the axis here I aligned. I have my zero axis of the lift coefficient aligned with the graphics. If I select the graphics, you can see also. I will move a bit on the left. Okay. So this is my zero axis on the lift coefficient on the graphics, and this is my zero axis on the picture. So I align them, I put them together, and same thing I do with the vertical axis on zero angle of attack. So this is my zero angle of attack in degrees, and here I have the same line in the graphics, in the chart. Just to show you again, this is my zero graphics in the chart. Okay. And then I make visualization of these points in the graphics, and I see how they correspond to the picture. For example, I already created 4 points here, 4 points experimentally. Let's assume I need some points here in the middle. What is the angle here? Approximately 4 degrees. So I will put 4 degrees. Okay, and how much is the lift coefficient? Is approximately 0.6.7. Okay, let's start from 0.6. Now this point does not appear, but if I click on my graph and I just extend the area of data from my graph, I see that this point already appeared. This point right here is not exactly on the experimental point. So I will just zoom and I will look carefully. Just I need to see numbers and same time the picture. Okay, like this and like this. So I need to move this red point a bit on the right, so it will be a bit bigger value of the angle of attack. So probably it will be not 4, but 4.1 or even more. I will put 4.2. Okay, so you see it's a bit moving this point here for 4.3. And I move upper. I need this point exactly in the middle of this square. So 0.65, and step by step I will approach to the center of my experimental point. And you can see that precision can be quite good. Oh, maybe 63. Okay, it's better. Precision can be quite good because the quality of the data from the book is not perfect. For example, I'm quite sure that this angle here should be 0, right? 0 angle of attack, and this step is 2 degrees. 2 degrees. So it should not be, for example, 4.3, but I'm quite sure that they measure it 4 degrees. But on the picture, it looks like 4.3. So we already have kind of misalignment or the error of recording of experimental data. And this is quite normal when we are transforming the graphical data into numerical data. If you do not have numerical data, is the only way you can transform this data. Okay, and one more point, just to be sure you understood, I will choose here was our 8.7 angle of attack, and I will take this next point here. How much it can be? Around 10 degrees, right? So I will put 10, and approximately it's 1.25. And I will again select my graphics and extend the range to plot the graphics. Okay, this point appeared again a bit distant from my experimental data, and now I will start to adjust. Okay, let's put 10.5 more, 10.6. Okay, maybe a bit more. No more, 10.7. Okay, and let's move a bit down this point, 23. And more a bit to the right. Okay, that's the experimental point. It's exactly in the center of my data. I know that there is an error, yeah, and we have to accept this error if there is no way to extract numerical data just looking by this instrument. We will always have some kind of error, and I hope this error will not be very big. It can be up to 5% is normal, is the normal value of the error, and it's quite acceptable. So this is how I transform the data from the graphical point of view to the numerical point of view. And not the whole thing. I will just, I would like to write for you the definition of the error, which I use to calculate. For example, for this lift coefficient, we will define the error CL, define it in the graphical form. Okay, G, it's what we see on the graphics, minus CL, what we can receive numerically. So it's basically how distant is the point from the graphical point, the numerical point, distance from the graphical point, and it will be divided by CL, but the maximum value of the CL. So once we are taking the difference, we have to always divide by its maximum possible lift coefficient. Okay, and it should be less or equal than 5%. You make this kind of estimation and you will easily obtain the error of your calculation. Why it's important to know the error of digitalization, let's say? It's important because then you will make a numerical simulation and you will obtain also difference between numerical results by Fluent and this data you took from graphics. And the error also must be similar to the obtained error from digitalization. I'm saying to you that this difference will always exist because it's not possible physically to match these 2 points. Always will have some kind of misalignment, right, or the difference. For example, if I'm looking to 0 angle of attack, this point right here, its lift coefficient 0.22.5. But look, if I write just 0.22, it's basically moved just on 1 pixel here, and it's still inside my square. So I don't know if it's 0.22, if I make 0.23, it's still inside my square. I moved a bit upper, but still inside my square. So it can be an error of my transformation from graphical to digital format. And easily I can write that this error in my case will be 22 minus 23 is 100, 001, this difference. And then I will divide by CL maximum, in this case is 1.6. Okay, and how much it will be, we can calculate. It's less than 1%, you see. This the error which I received just digitalizing this point is less than 1%, quite good accuracy. Same thing you can do in the direction of the lift coefficient, so point can move up and down, and same way point can move to the left and to the right. So it's not just the lift coefficient error, it's also the angle of attack error could happen. Okay, so because you can move inside this square a bit left, a bit on the right, and then you will have this difference error related to the angle of attack is alpha right minus alpha left divided by alpha maximum, something like this. And this is how you can calculate the alpha error. It's not directly important in this case, but it can be important when you are building a relation which everybody is asking now in the group, lift to drag chart or lift to drag diagram. I will add another comment here explaining the behavior. And as you may see here, there is a so-called equation 457. We did not come to this equation yet. It's actually too early to talk about this equation. Too early because we are still on chapter 1 and this is equation theoretical from chapter 4. But already anticipating, I will tell you that this equation is the line equation. And if we are trying to insert some line function, we can do it adding the line to our chart and additional data. We will see that all the behavior of the lift coefficient is going according to this line or very close to this line. I will just make a line here and draw the line. So what we can see that behavior of the lift coefficient will also follow close to the line, right? And the experimental points will be always close. It cannot go upper, lower this line. It always will be on one side of the line. Theoretical line is going higher because it does not take into account viscosity, for example, and boundary layer, these nonlinear processes. And the theoretical line is more simpler model of the aerodynamics around airfoil. So taking into account this viscosity and boundary layer, we have a line real lift coefficient lower. So this line will be a guideline for us to build experimental points, to put experimental points. Slope here, or the angle of inclination of this experimental curve, is always decreasing. It has some high values at a low angle of attack, and then this angle goes down. It decreasing, it reaches some maximum point, which is our stall condition, and then it goes down with the flow separation. And this happens for any Reynolds number we might find. Okay. In this particular case, it's just two different Reynolds numbers, but you know that for people who already found their experimental data, the behavior is very similar for all Reynolds numbers. Another comment I would like to give you is about discussion yesterday, which raised in the group about, okay, someone did not understand how to visualize or why we should make some validation of experimental data with some other experimental data, or if we get some experimental data, why we need to validate it with some other reference. So I would like to clarify one more time that look, this experimental data, for example, what I show you on these graphics is just 2 parameters. Actually, we can find the third parameter. It's 2 parameters. We have the CL graphics as a function of alpha, right? We have CD from another graphics, which I did not show you, but it exists for this airfoil as a function of alpha. And it has CM as a function of alpha also on this picture. This is what you have. And if you are very lucky, you find the CP distribution for various angles of attack. Okay, CP distribution for different angles of attack. If you are lucky, you get this from the literature. If you are not so lucky, you can just take Xfoil program and put your airfoil inside Xfoil. You can get always pressure coefficient distribution from the program. And this is also acceptable. I accept Xfoil results for the pressure coefficient distribution. It's not always possible to get from the literature, so you can use Xfoil, but just for CP, not for CL, CD, and CM. As a result of work 1, you must present not just these 4 parameters. You need to present other, for example, CA and CN and center of pressure, okay? And these parameters are not experimental data. Usually, you will not find all this list of data from the book. You will find just few in the book, and the others you must calculate. This is what I mean when I say calculate these parameters using formulas. Data can be represented in different formats in the literature. Sometimes there is a CL versus CD, okay, or lift versus drag coefficient. Let's see, L or CL versus CD, something like this, and you have your distribution. Always also possible. If you have a possibility to check if this data is correct, please do it, because you cannot just take from somewhere or different sources and use combining from different sources and use this data as already final result. I just give you one example. You see 2 different publications and you find very different lift coefficient in one publication from the other publication. So what you will do, what data you will accept from which is lower values or which is higher values, how you will evaluate what data is correct, what data is not correct. This is very important. And to know exactly what is correct or not, you must use probably tools of aerodynamics and try to calculate by hand something and see, okay, this looks real and this is not looking real. I'm talking about formulas at the beginning of the book when you convert one aerodynamic coefficient to another aerodynamic coefficient. Okay, this is what I was saying, that you need to validate your results, because if you see very different results from different sources, you need to use another one more tool to verify if this data is correct or not. Because if you present this and it will be not correct, and then you discover that you use completely wrong results, it will be a problem of person who used this data, who accepted this data. And it's you, and you need to know that this data is correct. So I'm trying to help you to determine what data is correct and what is not. So try to use not just one source, try to find more options, try to see what other people did, what they used for validation of their numerical results, respectful sources. I mean, publication from NACA, for example, publication from Institute of Aeronautics are always welcome, right? maybe you can use some kind of polynomial approximation for this function to describe, to make it more smooth, or spline function to describe. But do not exaggerate. Just make it looking nice, and then you will be fine. Usually, when you start to see some strange behavior of the curve, it's very suspicious in incompressible aerodynamics, because it's low energy flow, low energy aerodynamics, and it cannot create high perturbations of the flow. So it must be really nice behavior of the flow properties. To describe the question of maximum flight velocity, I will need again to draw my aerodynamic coefficients. I will make two coefficients here that enter into calculation of the maximum velocity. First coefficient that we already know is the lift coefficient. Its behavior like this. This is alpha, this is CL, and the drag coefficient. Behavior of the drag coefficient is like this. It has very low values or minimal values close to zero angle of attack, and it has its maximum values when the flow starts to separate, has a rapid increase of the drag coefficient. Okay, so lift coefficient and drag coefficient. As we already saw, the stall velocity, which we are calculating at point of zero angle of attack, is v stall equal to square root of 2 weight of the airplane, which is the same as the lift, right? Divided by CL minimum, or CL alpha 0, and then density and yes, the area. Yes. Of course. Yeah, I remember that there was something more. Thanks for reminding. So this is the stall velocity from point of view of the lift coefficient, and for this the maximum velocity we're using. Stall velocity is crazy. Maximum velocity. This is just from the point of the weight of the airplane, but we need to remember that we also install some engine on the airplane which accelerates, right, creates the thrust. And the thrust force is opposite to the drag force created on our airplane. And the CD coefficient is responsible for the drag description, right, dimensionless drag. And the thrust is equal to the drag when the airplane is not accelerating anymore. And this is exactly our case. We accelerate until our maximum velocity. We are not accelerating anymore, and thrust of the engine is equal to the drag. So we cannot install infinite power engine on our airplane. It's always limited and known, the value of the power. And actually, as we already discussed before, is defined by the lift to drag ratio and is proportional to the weight of the airplane. Bigger is the weight of the airplane, bigger should be the thrust of the engine, according to lift to drag ratio, or CL to CD coefficient ratio. And same way as we wrote this formula for maximum velocity, we can define it from the point of view of the drag and thrust. So I will write that V maximum here would be equal to the square root of 2 thrust of the engine divided by CD at alpha 0 and the density and the area. Same parameters as we had before, same density and same area for both formulas, weight of the airplane, thrust of the airplane, and CD at alpha 0. And these two formulas actually are equivalent to each other, because once we are defining constant lift to drag ratio, from one formula we can easily go to another formula. But what is important here, if we analyze the second formula, we will see that this CD for alpha equal to 0 is actually the minimal possible coefficient, minimal possible drag coefficient. So it means that we can reach maximum possible velocity at these conditions. Since it's minimal, right, in the denominator, the ratio in this formula is having its maximum value, so we are reaching maximum possible velocity. So this is actually why we usually work on maximum velocity with zero angle of attack, because at this zero angle of attack, drag coefficient has its minimum value. Okay, so the question of the minimal possible thrust is working here, and minimal power consumption, fuel consumption also is exactly at point of zero angle of attack, or very close to zero angle of attack. Depending on the structure of the airfoil, design of the airfoil, this point of minimal can be shifted in one or other direction, but not so much. So we always are talking about values of maximum velocity and angle of attack close to zero. So it optimizes the efficiency of the flight and results in a maximum possible flight velocity, right? Sometimes flying faster is better in application of delivery, in application of logistics, in application of military cases, etc. So we are talking just simplifying. Now it's just simplifying because we did not discuss fuselage, we did not discuss the tail, anything. Just the airfoil vessel. Look, we did not even discuss the wing by itself. It's not the wing yet. It's just a airfoil profile, and inside the wing will be different things which we must take into account. It's just very simplified way to explain you the physical process of maximum velocity, right? Okay, but it's a very interesting question. I agree that in future, once we advance in aerodynamics, you start to see more and more bigger picture, and you will add also other physical objects and physical processes that happen inside the flow, and it will help you to understand. But from the beginning,
entre fuselagem, profundor e leme, né? E asa, né? Arrasta tudo, né?
Yes, there are many questions here. And also, look, the wing by itself is not something simple for now. It's not just rectangular surface, right? It can be a swept wing. It can be twisted aerodynamically. For example, when angle of attack is changing from the center of the wing to the tip of the wing, is changing angle of attack, optimizing performance of the airplane. Is very common that angle of attack is changing. So we are talking about very simple concept, the initial concept, let's say, and then we will advance. But this is nice that you ask, because it already opens this discussion for future, the discussion for future, which is very important. Very nice. But there is a one point of strange behavior, the maximum, right?
Left axis.
At 17 degrees, it's a very strange behavior of all coefficients. It must be smooth behavior of, let's say, smaller, I think. Lift coefficient must be bigger, drag coefficient must be a bit smaller, momentum coefficient. I think something is a bit strange, but it looks nice.
The scale of the right axis with CD and CM is smaller, so the value here is 0.4, while the value here is 1.4.
Yeah.
I tried to do that because in the article, let's see if I think it's opened here. The CD and CL cross because they are in different scales.
Right.
So I tried to replicate it, and I also used spline because, well, they don't really connect with straight lines. Then I was thinking, and I didn't use spline on all of them. I tried to look for another interpolation because my CN and CA were weird right here. For the CA, I was having problems with spline. It was making weird curves in here.
You know what I recommend you? Just cut after 17 degrees. Do not show what happens after 17. It's actually not interesting for us. There are no airplanes or airfoils working with the flow separation. It's absolutely useless to work in this region.
For the scale to be
until 17. So we work only until 17 degrees and finish. This part of flow separation is interesting for scientists who study the question of turbulence and related topics. And vortex separation, for example, different turbulence models. But for practical application is not so much important.
Okay, it's because the article I found was on a variable density. Tunnels was confirming tests, so I was thinking about how I'd compare on work to the data for things like CL and CD when I have data that is in compressible flow. Not really compressible, but having the experiment accounting for that.
Okay, okay, and very nice, very nice.
I had some doubts also on here. I tried to plot CP kind of like the graph with it going down up to 100%, plotting it in percent.
CP is what here? What is CP
line.
here? What is CP? Center of pressure. Center of pressure is different from pressure coefficient, right? You understood, right?
Yes.
Okay.
Yes, I still have to calculate it. It wasn't on my article, so I'm happy to see I don't have penalties for using Excel.
Oh, it's quite good values, quite good values.
And I was thinking about how I'd compare the data I got from the LD ratio and the ratio of the data I got from CL and CD. I think it was kind of close, but there are 2 points which are a bit distant.
Yeah, you just show and describe. Show and describe. In this step of work one, we cannot, how to say, justify from the physical model point of view, because you simulate physical model only on work two. So now you say that this happened, right? This result difference between 2 points happened, and we expect in the numerical simulation something in the middle of this point, right? But I think that the black line is more realistic here. And looks like more smoother. Usually aerodynamics is giving very smooth curves.
I was trying to use spline here too, but I had problems in this region. It was with weird curves.
Yes, I know. You probably need to use another type of splines. There are many different types of splines, and there are splines that do not cause these kind of problems. I think it's Akima spline. Akima spline that is respecting the function extremums. So it doesn't go over the maximum or minimum of experimental points. Try to find the Akima splines. If it's implemented in the MATLAB, you can do it.
I tried PChip. I looked for some other cubic interpolation methods, and I think PChip worked all right.
Yes, you know what? Sometimes even acceptable to make just linear function, just lines between points. Because this kind of approximation, when we go to second order, third order, and the fourth order, like for this spline, for example, it always linearizes solution. And real aerodynamics process, they are not so simple and they are not linear, so they do not go according to the spline function.
All right.
It's even good to put just lines between points, straight lines, and then it's acceptable.
So concluding here, I should cut my result up to 17 degrees.
Yes, I recommend to cut because we will never work in this region.
And I should also use the same scale on both axes, left and right.
No, not obligatory. It's good.
Right.
It's a good scale. Left scale should be different from the right one if you work with the different values. It's very, very normal to have different scales.
Okay.
So I even prefer that you have different scales on the left and on the right because it represents better small values and big values. And sometimes when we will work, for example, with pressure distribution, I even accept when you present in logarithmic scale. And it demonstrates data behavior, parameters change in a much more representative way. Logarithmic scale should also be considered for some data which changes in a very big amount of times. For example, you show some kilopascal and you show some pascal. When you try to combine this, only possible in logarithmic scale. But we will go step by step to this question, and I think it's too early to give you a lot of information right now. But it's nice that you ask. Okay.
When I plotted the graphs, I was thinking about which ones I should plot together. What I did was CL, CD, and CM with the first, and CN, CA, and just let's see.
No, it's not so important. Just try to combine some graphs together, not to spare in the whole work, so it will not have like 100 pages. Because one time I received the work of student, work one, more than 80 pages, and it was a hell to check everything. It was very difficult.
There was another thing I was thinking about. When there is written in the instructions for work one that we should use ABNT, is it just for formatting, like the font, the size,
yeah.
type?
It's a standard requirements for any UNB report, so it's a standard.
I was just thinking that there are different ways to be strict about ABNT, because sometimes we will have a capa, contra capa, índice.
Yes. Yeah, no, use the simple format. Do not exaggerate. This report should be short. Do not exaggerate. You can even do in overleaf, for example, if you don't, if you want it to be formatted automatically, just use overleaf or any LaTeX format, and it formats all according to ABNT. You do not need to worry about things. When you make graphics, please try to make it looking nice. So font should be big enough, the points should be clear, okay, because sometimes people deliver work with very, very small numbers, even not possible to see on a big monitor what are the values, and very difficult to understand if it's correct or not.
Okay, I was thinking if for work 2, comparison with work 1, we should plot those graphs independently against the simulation results.
When you will do simulation, you put both on the same plot, right? You put simulation and experiment on the same plot, and not just this. You will compare the numbers, calculate the error between points, difference numerically, and you will show numerically the difference.
Okay, with error, you're talking about the difference between the two?
Yes. So we have this error of digitalization, we have the error of simulation. Always these errors must be considered, and then the final error will be something of total of all errors you have in the system, and it's normal to have error. I mean the error in a good sense, right? Difference between experimental and numerical data. It's not the error of work. It's just this kind of error when you do the same work using different methods. Ask about the pressure coefficient distribution for different angles of attack, right? And Reynolds number is small, like 13,000 more or less. The Reynolds number affects only in this case on the viscous part of the aerodynamic properties. It means that what will change with the higher Reynolds number significantly will change the drag. But pressure coefficient basically will not change because pressure has a small influence on viscosity change, or Reynolds number has small influence on the pressure coefficient distribution. So it's okay to use pressure coefficient for small Reynolds number. It will basically the same from aerodynamic point of view for smaller and higher Reynolds number, if it's not so much critical, if it's not huge values of Reynolds number. Of course, I mean when it's not transonic, becomes transonic flow or supersonic flow, then CP coefficient will of course change significantly. But if we are working with incompressible flow, any value of Reynolds number probably will result in basically same pressure coefficient distribution. So you can use it. Another part which will suffer is the shear stress. Shear stress is dependent on the Reynolds number, but not pressure coefficient. Just the shear stress. If you try to compare, for example, shear stress coefficient, then you need to follow the same Reynolds number. But for pressure coefficient is not important.